This video lecture is meant to help you understand a little bit more about the electron cloud model and the quantum mechanical model, which describes with a certain probability where we can find electrons. And scientists have tried to come up with a way to describe mathematically where electrons exist. We're going to not get bogged down in the mathematical equations, so we're going to try to do this as conceptually as possible, which is a little bit difficult to do. But we're going to start off here by trying to describe where we can find electrons in the atom using what we call an orbital diagram. You're looking at an orbital diagram. You'll see boxes which represent what we call orbitals. You can think of them as kind of little electron clouds, but they're referred to as orbitals. So each box is an orbital. And you can see here that there are some numbers and some letters associated with each of these orbitals. The lowest energy is the first energy level, seen down here at the bottom where it says 1s, right here. Then the second energy level is represented by these orbitals. The third energy level is represented by these orbitals. And so you can see that as you go up in energy, there are more orbitals involved in each one of those levels. We have arrows here. Arrows represent electrons. And if we were to start with hydrogen, hydrogen has an atomic number of 1, meaning it has 1 proton, so therefore it has 1 electron. Remember, protons positive, electrons negative. One of each will make the atoms neutral. So in a neutral atom of hydrogen, there will be 1 electron. We're going to show that as a single arrow pointing upwards. We're going to put it in the lowest orbital available, which is the 1s orbital. We would then record that as 1s with a superscript 1. So this superscript refers to the 1 electron. The 1s refers to the orbital where we can find that electron. Helium with 2 electrons. We're going to show the second electron in the same box, the same 1s orbital. This time, however, you'll make the arrow point down, and you will record that in what we call, this is called an electron configuration. The 1s orbital now has 2 electrons in it. Lithium with 3 electrons. Well, that third electron cannot fit in the 1s. The 1s is full. When you have an up arrow and a down arrow, 2 electrons, that means that orbital is full, there's no more room. So the third electron has to go into the next energy orbital level possible, and that happens to be the 2s. So we'll show that third electron, as an up arrow, and we'll record that configuration here as 1s2, 2s1. Beryllium with 4 electrons. That fourth electron, there's room in the 2s orbital. We're going to show that as a down arrow, and we're going to record it as 1s2, 2s2. 2 electrons in the 2s orbital, 2 electrons in the 1s orbital. Boron with 5 electrons. That fifth electron can't fit in the 2s. It has to go to the next energy level available. We're going to call it 2p. And you see here in the 2p there are 3 orbitals available. We're going to put that electron in the first box, the first orbital. We're going to show it as an up arrow, and we record this as 1s2, 2s2, 2p1. Carbon with 6 electrons. That 6th electron is going to go into the middle of the 3 orbital boxes, the middle orbital there. You're going to find out that electrons do not pair up until each of these orbitals within a sublevel here have at least 1 electron. So we would write this as 1s2, 2s2, 2p2. So this down here, this electron configuration, is essentially a summary of the orbital diagram. Nitrogen with 7 electrons. That 7th electron now has to go into that third available orbital in the 2p sublevel. So now each of the 3 orbitals in the 2p sublevel each has 1 electron, and we would shorten that down into the summary 1s2, 2s2, 2p3. Oxygen has 8 electrons, and so that 8th electron will now get paired up in that first orbital, that first box of the 2p sublevel. And we will show that again with a down arrow. Notice that there's only an up arrow and a down arrow in each of the orbital boxes. We'll summarize this as 1s2, 2s2, 2p4. Fluorine with 9 electrons. That 9th electron will get paired up in the middle of the 2p orbitals. We'll draw it as a down arrow, and we'll summarize that as 1s2, 2s2, 2p5. Definitely seeing a pattern starting to emerge here. Neon with 10 electrons. That 10th electron will now be in the last available spot in the 2p sublevel. We'll put it as a down arrow in the 2p orbital, and we'll summarize this as 1s2, 2s2, 2p6. Of note here, you'll see here that now the second energy level, the 2s and the 2p, are now completely full. That makes for a very stable configuration. Neon, if you'll notice on a periodic table, the neon is part of the column that's all the way to the right. Those are called the noble gases, and they are non-reactive. They are non-reactive because their electron orbitals are completely full. They don't need electrons. They don't have too many electrons. They're just completely full and satisfied, and therefore non-reactive. We're going to continue to elements down on the third period of the periodic table, starting with sodium. Sodium's all the way to the left on the periodic table in the third period down. And so sodium with its 11 electrons, that 11th electron has to go into the next energy level up, which is 3s. Again with the up arrow, and summarized as 1s2, 2s2, 2p6, 3s1. Magnesium with 12 electrons. That 12th electron will fill up the 3s orbital as a down arrow, and we'll summarize that as 1s2, 2s2, 2p6, 3s2. The next element is aluminum with 13 electrons. The 13th electron will have to go into the 3p sublevel. And then notice again, now that we're in the third energy level, but the p sublevel, with p has these 3 boxes. All right, so we'll put that 13th electron in the first box as an up arrow. We'll summarize it as 1s2, 2s2, 2p6, 3s2, 3p1. You'll notice the pattern continuing on here with silicon. Silicon has 14 electrons. That 14th electron has to go into the middle box. We don't double up electrons until each of the orbitals in a sublevel are at least half filled. 1s2, 2s2, 2p6, 3s2, 3p2. Phosphorus with 15 electrons. The 15th electron will go into the third orbital of the 3p sublevel as an up arrow. 1s2, 2s2, 2p6, 3s2, 3p3 is how we summarize that in that electron configuration. Sulfur. This electron, 16th electron, will now pair up with into the first orbital of the 3p sublevel as a down arrow, and we'll summarize the orbital diagram in this electron configuration here: 1s2, 2s2, 2p6, 3s2, 3p4. Chlorine with 17 electrons. The 17th electron will go into as a down arrow in the middle box, the middle orbital. And we'll summarize it as 1s2, 2s2, 2p6, 3s2, 3p5. And argon. Argon has 18 electrons. The 18th electron will go as a down arrow in the third box of the 3p sublevel as 1s2, 2s2, 2p6, 3s2, 3p6. Notice here argon has a full 3s and a full 3p. When that happens, you'll notice a pattern that argon is in the last column all the way to the right of the periodic table, just underneath neon. Argon is one of those noble gases. It's non-reactive. It is non-reactive because it has a full 3s and 3p orbitals, sublevels. Okay. Please notice, this is where we're going to stop this for now, but as we go to the fourth period, things start to get a little goofy, a little more complicated. You'll notice that the next energy level up is 4s, but then 3d sneaks in there before the 4p, or 3d has a little bit more energy than the 4s. but a little less energy than the 4p. So it starts to be, there's some overlap that starts to happen. The other interesting thing that you'll notice is the D sublevels. Instead of having 3 orbital boxes, there are 5 orbital boxes. You'll notice over here the F sublevels have 7 orbital boxes. So as you get into these bigger elements with more electrons, things start to get a little more complex in electronic structure. But we're going to leave the 4th period elements for a different day. So right now what we've done, you should have a big piece of paper filled with orbital diagrams and electron configurations for the elements in the first 3 periods of the periodic table. Hopefully you'll see, you've noticed the patterns that have emerged, and we'll talk about these patterns and what they mean in terms of properties in upcoming lectures. This concludes the video lecture on orbital diagrams and electron configurations for elements in the first 3 periods.